everyone. We are going to present our project on visual question answering using CLIP, a neural network which efficiently learns visual concepts from natural language supervision. How do humans make sense of the visual information around them? Well, this leads us to motivation of this project as to understanding visual information using natural language and using the tight coupling between vision and language. How would machines also be able to perceive the visual information around them using natural language? We want the machines to infer the visual information using natural language and answer visual questions. VQA is a task of selecting one of many possible answers given an image and a question associated with the image. We are using the VQA V2 dataset, which has around 4 million question-answer pairs. Here are some examples of images and question pairs. For example, in the top left image, the task is to answer the question like what colors are her eyes, what is the mustache made of, etc. So with this project, we want to explore the ability of machines to understand and communicate the understanding through question answering. We believe that solving this problem will have societal advantage and will help visually impaired to understand and answer questions. The challenges associated with this task is that it is difficult to train such models and it is an expensive process. So we want to leverage the pre-trained data for vision and language for the VQA task, and hence we resolved to use CLIP, which released a large self-supervised trained model on a huge corpus of image text pairs, which is also used for various vision and language tasks such as zero-shot image classification, zero-shot text-to-image generation, etc. So we want to propose two baselines. First is the supervised baseline that learns a two-layer MLP for question-answer alignment in order to bring QA prompt embedding closer in image embedding space. Second, a simple zero-shot baseline that uses a simple QA prompt to enable zero-shot transfer using CLIP. First, we look at our unsupervised approach where the CLIP model is frozen and we generate a question-answer prompt of the form question, question, answer, answer. We then generate a text embedding for this prompt by passing it through CLIP text encoder and pass the image through CLIP image encoder. Finally, we use a cosine similarity over these embeddings to predict the best answer matching the query. Our assumption for this baseline is that CLIP has semantically richer embedding, so it should be able to perform well in zero-shot framework. Second, we propose a supervised approach where the CLIP model is frozen and the only trainable module is a question-answer model, hence efficient and quick training is possible. To improve our zero-shot question CLIP baseline, we propose a question-answer embedding alignment approach. We sample the batches for training similar to contrastive style training where we sample one positive example and n-1 negative examples for each question. Sampling batches in this form allows our model to learn to map embeddings for relevant answers closer in embedding space and push the embedding that are not relevant far apart. We try two versions of QA alignment model. First, we learn a single two-layer MLP which takes question and answer embedding as input. We use this joint learned representation as a query representation for frozen CLIP image representation as shown in the figure. Next, we concatenate joint embedding, question-answer embedding, and image embedding and pass them through a linear layer that learns similarity of these representations instead of using simple cosine similarity. The intuition behind using an additional linear layer is that it will allow us to learn a joint representation space for QA and image for VQA. As a simple upper bound, we set up a vanilla n-way classification baseline using frozen CLIP representations. We use a simple learnable two-layer MLP that takes image and text CLIP embeddings as input and learns to predict answer using n-way classification head. This baseline leverages rich CLIP representations and learns a simple mapper that can map question and an image to answer. We compare our approaches against two state-of-the-art baselines. First is the QIP, which explored directly prompting the CLIP models for VQA task. They used a question text, answer text template together with prompt engineering of image classification to prepare prompts. The resulting prompts are irrelevant of questions. The second is TAPC, which uses a combination of automated template generation and common sense answer filtering to improve zero-shot VQA performance. They use a large language model and dependency parsing to automatically convert the question into a template. For example, a question, "What is the species of the flower in the picture?" is converted to, "The species of flower in the picture is mask." As common sense, the species of flower can never be a vase. TAPC then leverages pre-trained language models to filter out less likely answers, as it would have positive influence on final question answering performance. Once TAPC gets a filtered set of answers, they replace the mask with all candidate answers to generate candidate prompts. For experiments, we use a subset of VQA dataset that was sampled using a simple heuristic. We only consider questions that focus on the color subcategory. Our sample has 268 unique possible answers. First, we compare performance of our zero-shot baseline across different prompts. We try 3 different prompts and we see that prompts with simple question and answer appended performs better compared to a prompt where we use question and answers as separate tokens. Additionally, we also find that increasing number of candidates in zero-shot transfer leads to worse performance. This is intuitive as adding more samples introduces more noise in our evaluation. Next, we compare ablations of different numbers of negative samples used for our supervised baselines. We find that increasing number of negative samples in training leads to large drop in performance. We hypothesize this is because of large class imbalance. In order to mitigate this issue, we can use a weighted loss as our objective. We leave that as part of future work. Finally, we compare our proposed approaches with the supervised upper bound. We use the NV classification baselines as our upper bound. We find that our zero-shot baseline performs approximately 47% worse compared to supervised upper bound, and our proposed supervised baseline performs approximately 25% worse. Our zero-shot baseline can be improved further by using a better candidate sampling strategy, and our supervised counterpart shows promising results, but there is still scope for improvement. Finally, we compare our proposed baselines with 2 state-of-the-art baselines, QIP and TAPC. Both these approaches are zero-shot VQA baselines. QIP uses QA irrelevant prompts and achieves 21% accuracy, and TAPC uses common sense filtering with template generation to improve zero-shot candidate prompt generation and selection and achieves 39% accuracy. Both these approaches are worse compared to our supervised upper bound, demonstrating that current state-of-the-art baselines can be further improved. Our proposed vanilla zero-shot baseline performs 19% and 37% worse compared to both SOTA approaches. Our QA alignment approach, on the other, beats QIP by 3% and performs 16% worse compared to TAPC. Finally, we discuss some limitations of our approach. Firstly, for our vanilla zero-shot approach, simple prompt without any common sense filtering and prompt engineering. And secondly, it has low performance due to naive answer candidate selection heuristic. For our second approach of question-answer alignment, we have naive candidate answer sampling strategy and simple prompts, and improves over manually engineered prompts as shown in QIP, and it suffers from noisy samples. And lastly, our NV classification has better results than TAPC. It suggests that the need for more sophisticated zero-shot baselines is needed. Thank you.